shouldn't be on, but what we talk about will be. Okay, here's our agenda for the day. We've already done part of it, but let's kind of run through this stuff really fast, because contingency tables and independence is where we're going to spend a large part of our time. If you read this the chapters last night, this is going to be a recap of all that, but hopefully it's not a waste of your time. So let's start going through. Let me move this out of the way. All right. So chapter 2 vocabulary, again, don't worry about writing the stuff down. I just wanted to talk about it for a second. Context, what is the data about? You need to include that all the time. Writing numbers down doesn't mean anything in stats. You need to give the context. A case is an individual in the data, and it can be a person or an object. The population would be all of the possible cases. Now, well, I'll talk about that more. So it's all the possible cases are going to be represented by a sample, and that's going to be a selection from within the population. This is all going to be stuff that we're going to come back to in great detail later, but it's just good to have that basic understanding at this point. And the population is not always going to be obvious, and that can actually cause some problems down the line. So just kind of be thinking about that as you come across problems like this. Variable, that's going to be any characteristic about one of the cases that can change from case to case. Now, the cases themselves are not variables. And lastly, this doesn't need an explanation, but just make sure to include your units for quantitative data. If it's a table, you might just at the very top say weight in pounds, so we know what is being measured. Okay, hopefully basic stuff. If I see hands raised, I'm going to be, if you see me looking off to the side, I'm checking to see if hands are raised or anything in the chat, but otherwise I'm going to keep moving through. So the big stuff from chapter 2 is the difference between categorical and quantitative. So categorical, here are some things about it. We're dealing with counts. And what I mean by that is if you have a category, like favorite color is red, then the only thing you can do with data from that categorical variable is count the number of people who have a favorite color of red or blue or green. So you can count them up. Okay, so we're always dealing with counts there. So kind of think of it that way. And it can be numerical. So here's where I want to go back to that bell work problem where I asked you guys how many siblings you had. Normally, number of siblings, what would you call that? Just put it in the chat. Would that number of siblings, would it be quantitative or categorical? So a lot of you are saying categorical right now. And there we go, there's quantitative. If there was no other context given, I would say normally it's quantitative. How many siblings do you have? It's a number. And normally I would think of it that way. But the way it was, and the reason some of you are saying categorical, when I asked you the question in the bell work, I turned that quantitative variable into a categorical one. You had to figure out which category you fell into. Were you in the category of 0, 1, 2, or 3 or more siblings? So it's kind of look at the situation and see how it's being used to determine if it's categorical or quantitative. Okay, so hopefully that example makes sense. All right. And well, that kind of goes to this point. Some data that appears to be quantitative can be categorical depending on how it's used, like in our example today. Okay, and then we have quantitative data. The key thing here is, does it make sense to take an average of this? So if I asked you to get the average zip code for all the people in the United States, that would make no sense. But if I asked you to get the average weight of everyone on, the Arizona Cardinals, that number would make sense even if you don't necessarily know why you'd need it. But yeah, averages if it makes sense to take an average of it, then it's quantitative data. It must be numerical, and it must include the units. Pretty straightforward. So those are the kind of key takeaways. Later on, identifying whether it's categorical or quantitative, kind of, you're not going to like shout it out to people, but just in your head, identifying if it's one or the other is going to determine what kind of analysis we use. And you know, if it's categorical, that's going to tell us right off, it can't be this, 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 or this test. It has to be one of these 3 tests, you know, something like that. And that's all for later in the year. Okay, frequency tables. Now we're jumping into all the different types of displays that we saw. I'm going to go through this, except for some of these we'll spend more time on. All right, so it's hard to see relative differences, but it's easy to find the numerical data. We've got the numerical data right here. Having the tally makes it easier to see the relative differences, but a lot of times we're not going to have that. For relative frequency tables, these are good for proportions, but if they don't include this column that shows the actual counts, then its usefulness is limited because we might not know how many people were counted up or how many cases were counted up. All right. Relative frequencies right here must add up to 1. They don't have the total here, but if you add up all those relative frequencies, it does add up to 1. And if it doesn't, you're in trouble. You've done something wrong. Okay. And just as a note real quick, as we're going through, I told you to have pen and paper, pencil and paper. Just, you know, if there's anything that you're like, okay, I want to remember that, you can write it down. But, you know, you kind of figure out what makes the most sense for you. Bar charts, good for visual comparison, but it can be hard to figure out raw numbers, and the categories do not have to be mutually exclusive. The bars must have equal width and must have gaps between them. So you can see the gaps between the bars, and all of them are equal width. So the thing that second one, the categories do not have to be mutually exclusive. What I mean by that is in this example given, we're talking about races, and it gives multiracial as an option. So, you know, you would fall into one of those categories, right? But let's say it was instead favorite ice cream, or not favorite ice cream, but just ice cream you like. And I gave you chocolate, vanilla, strawberry, all these different flavors. And you're like, I like chocolate, I like vanilla, and I like strawberry. And you kind of reported that. These don't have to be mutually exclusive. You could, as an individual, you could like chocolate and vanilla and strawberry, and you could be counted in all 3 of those. So that's what I mean. If it's mutually exclusive, like this one is set up, then you would only fall into one of them. But in a bar chart, it doesn't have to be set up that way. Okay, hopefully that's clear enough. This is actually for bivariate data when you have 2 categorical variables, but it's called a side-by-side bar chart. And we'll actually talk about that more a little later, but they're bar charts. You can see that they're separated. Okay, pie charts. They gives a quick visual difference of relative proportions. The data must be mutually exclusive here. Okay, and that's because the pie represents the entire population. So you couldn't have a pie chart of all the ice cream flavors you like, because then you might have 100% of people liking chocolate, 100% of people liking vanilla, and then if you put that into a pie chart, you have 200% shown there. That doesn't make any sense, right? They can be hard to read, especially if there are too many slices or if the percentages are close. And honestly, pie charts are just the worst. Don't use them. You will see them. You'll need to know how to interpret them, but they're awful. Don't use them. This is one that's, as far as pie charts go, not awful, because it includes the data. So some of these, like, if I didn't include these numbers here, and they didn't have it kind of in descending order, well, it's not exactly descending, but if I didn't include this stuff, you wouldn't visually know necessarily which is bigger, Internet Explorer or Firefox. You might say Internet Explorer, but you know, it's not easy to tell. Okay, now these pie charts are okay to use. All right, just a little pie chart humor in there. There are plenty of pie chart memes for the nerdy inclined people out there. Some of them are not school appropriate, so if you're interested in this more, you can look around and find those. All right, so pie charts are ripe for humor. Okay, the area principle. And again, if you read, this is recap of stuff we were reading. So in bar charts, make sure each bar has the same width, and don't use images to represent the height of the bars. And we'll see an example in just a second. In pie charts, show only a two-dimensional view of the pie, never a 3D isometric view. That means like at an angle. Also, don't use pie charts. So this is this isn't the worst example, but this is an example of what not to do, because when you tilt something, then it skews our sort of the way our brains see the relative differences. And now these two might appear in volume to be a lot closer than they really are, or not in volume, well, but in area on the surface. Okay, and this is a truly awful chart. Notice that the scale starts at 5 foot and goes up to 5'7". So the scaling here is way off, and we'll talk about that in a second. And the tallest is 5'5", the shortest is 5 feet, but the way they did this makes these Indian women look just tiny, you know, like babies. So really bad to do that. You want to make sure that you construct your bar charts like we talked about. So no. All right, this is other guidelines. You want to make sure that labels and scales are not deceptive. Sometimes it's not intentional, sometimes it is. So look at this real quick. And if someone is brave enough to speak, what does this story, or what is this chart trying to show us? What do you think the story behind this chart is? Maybe I could ask it this way. What end do you think the people who provided this chart, what do you think they're trying to accomplish with it?
I almost want to say like global warming, like the temperatures going up over the years, something like that.
Yeah, maybe something like that. Of course, the story overall tends to be, does it seem like it's going up much or down much?
It's kind of just going up and down all over the place.
Yeah, it kind of starts and stops at the end at the same place. It goes up and down a bit, but that seems to be the story of this chart. Now, if we look at a broader time scale, you can see where this data was pulled from. It was pulled from these years with that beginning and that end. And in this case, I think it's fair to say, because this was actually used somewhere, maybe in a congressional hearing somewhere, I don't know, but I think it's fair to say that this is being deceptively used to try and show that temperatures aren't changing. And when you look at a longer trend, you can see that there is something going on. All right, so this one would be intentionally deceptive. Sometimes we can be unintentionally deceptive when we just don't know that we're not including enough information. And if we had more information, then that would change our conclusions, right? So I don't think we need to say more about that unless anyone had questions. All right. Okay, and contingency tables. This is where we're going to spend some time. This is sometimes called bivariate tables, bivariate data, and that's because it's two categorical variables. And you might also see the name two-way tables. If you read last night, and hopefully you all read, this might have been where you had to stop and like reread stuff and really make sure you understood it. And we're going to practice with that today. So I am going to have you, and don't leave right away, I'm going to put you into breakout groups in just a minute. This is where it always acts weird on me, so let me do this. Nope, go back.
Good, I love rain.
Okay. So, okay, in a minute, you're going to do breakout rooms. And what you're going to be doing is going to desmos.com. You can just look up Desmos and don't leave right away. Your code that you're going to use is, and I'm going to put it in the chat. So that's where you're going to go, and you're going to use the code when you get there. Need to move something out of the way. 5XQGV. Oh, sorry, I sent that privately. I'm going to send it to the whole group. All right. There's the link, and that's 5XQGVZ. And when you get there, the last thing before you leave, well, two things before you leave. You are going to finish slide 6, then stop. All right, so don't try and do all 17 slides. Just go to 6 and then stop, and we're going to finish it out as a group. And secondly, let me put you into your breakout groups so that you can join that before you leave. All right. So rooms are open, you can join them, and then you can navigate over to Desmos and work through the first 6 slides. Do you know how to join, Sam? You're muted right now, I can't hear you.
I didn't see the link in the chat.
Okay, it's desmos.com. I can resend it.
Okay. And will it still be there when I go into the breakout room?
No, you might want to, well, and you can just remember desmos.com and navigate there. So yeah.
Okay. Got it.
So you guys finished slides 1 through 6, and I wanted you to stop here. So why is it called marginal distribution? If you guys want to unmute anyone who's brave enough and tell us why.
Because the power, or like, it's distributed between certain margins of people. It's not affecting every group the same.
It's actually a little more straightforward than that, though that's a good thought. It is.
Is it just like a portion of the total?
It is like the marginal distribution is showing proportions of the total. So that is what we mean when we say distribution. But why marginal? All right, might have scared people off from answering.
It's like added rows and columns to a table. It's not like the actual table. They added like the totals and stuff.
Okay, and I think you're kind of getting toward the answer here. When we're talking about the marginal distributions, we're talking about these total columns or rows. All right, and notice where those are on the table. It's at the margins. So that's really why it's marginal. So hopefully that'll help remind you if it's asking what's the marginal distribution of race or of force level. It's saying we've got these numbers right here that we can just do the 1,000, like in this case, 1,743 divided by 3,164. And this is showing us, in essence, it's a relative frequency table that has 2 variables on it. So if we got the relative frequency of Black suspects, Hispanic suspects, and white suspects, we would be able to break this down and see how the 100% of the total here is broken down by race. Okay, so does the margin idea make sense for you guys? Okay, and that is in contrast to the conditional distribution. Didn't go. And this, I'll read this, but I'll tell you, this might not help you. A conditional distribution is a probability distribution for a subgroup. In other words, it shows the probability that a randomly selected item in a subgroup has a characteristic you're interested in. Those are just words to me, okay? And maybe when you're looking at that, it's the same for you. So I'm going to try and make sure it's really clear. So we have our two-way table. And what we're talking about now is what is the distribution of force level used on the condition that the suspect is Black. So what that means is that I'm holding this condition that we're only talking about Black suspects. Okay, so that it helps me think of it that way, like on the condition that the person is Black, on the condition that the person is Hispanic or white, what is the distribution? So now, rather than comparing this 1,371 who had no force used to the total down here, so rather than that, I'm just going to compare it to, hold it to the condition that they were Black. So out of 1,743 total Black suspects that were stopped, how many of them had no force? Well, I just do that division. And I believe the number here, I'm not going to fill in the total table. I think it's 0.787. And if you guys want to calculate that to double check, I'm not going to go through all the distributions. But, you know, we could do all kinds of conditional distributions here. Because I could say, what is the race of the suspect on the condition that higher force level was used? So then I'm talking about this row right here. On this condition, I could break it down and I could say 109 out of the 199 total for that row were Black. Okay, it depends on what analysis we're doing, how we would kind of approach that. But does this idea make sense on the conditional distributions? Okay, so we can, as long as we understand how to get those numbers, let's not take the time right now. I think if I click check my answers, no, it doesn't tell me. But, you know, let's just solve one of them together. I'm going to have you guys do it. What is the conditional distribution for white? But just tell me hands being used on the condition of being white. And you can put it in the chat if you want. And go ahead and give it to 3 decimal places when you type that in. Okay, there it is. I'm seeing it. All right, now we could fill in the full table. We're going to see this table filled in a minute. So just for your time, I'm not going to make you do all of that right now. Are there any questions? And if I don't see hands up or anything, I'll assume we're good. We can come back to it if there is a question. All right, let me clear my drawing. So we should have the number 844. And what does this mean in context? So I'll go ahead and tell you where that is. That 0.844 goes right here, 0.844. So can someone tell me what that 0.844 means if you were to say it? Yeah. and I'll get you started. 84.4% of ...
84.4% of all white people who were stopped had no force used.
Perfect. Okay. Now remember, the condition is that we're looking at the condition that holds is race, but you got to be careful about that. That can be where it can get tricky. All right. So right here, so this is a yes/no question. I already clicked one of them, but you ignore that for now. A television commentator says police had no force interactions with only 260 white suspects. Meanwhile, a much higher number of black suspects, 1,371, didn't experience force. Clearly, black people experience force-free interactions with police more frequently than white people. Now, ignoring all of the kind of social answers that we might give to that, statistically, is that good analysis?
I would say that it's not.
And why is that?
Because the group of white people was a lot smaller than of black people that were stopped.
Okay, so when we consider the full counts, what is it that we're not getting in this analysis?
I was gonna say because the conditional distribution of force not being used was higher for those of the white demographic, then the analysis was wrong.
Okay, so I'm following you partially. So as far as, yeah, when we break it down by conditional distribution, I think, yeah, that's getting to the heart of it. So on the condition of race, I'll go ahead and tell you because we didn't necessarily, we did show these numbers, but not really. So this was 0.787, and this was 0.844. So when we compare the proportions or the rates, then we can see that there is a little more to the story, okay? So the whole point here is it good analysis? And yes, we're using some real world data that, it gets real, okay? So right here, we're not gonna do much with this, but you'll annotate in just a second. So you can see they run all the numbers, okay? We don't have to calculate that. And now we have a side-by-side bar chart showing this two categorical variable data, the bivariate data. And where in this chart would you find the 78.7% of black people who experience no force from police? And you can circle that with your annotation. Okay, you guys are finding it. Good job. I'm trying to remember if you'll ever need to create something like this. It is possible. I don't want to say you're not going to have to create a side-by-side chart, but most of the time you're just going to be interpreting stuff like this. And if you needed to create it, hopefully you feel comfortable with that. Let me clear all the drawings and we'll stop annotating now. All right, I want to go through some of the stuff. Okay, now we're going to be creating a segmented bar chart. I'm going to try and do this quickly just to make sure you know how to create it. You can see our breakdown of by race. And on the next page, they've set up a template for doing the segmented bar chart. So I'm going to look real quick at black, the black conditional distribution. 78.7 had no force used. 15.1% had hands used. 6.3% had higher force. So, and make sure you're not annotating right now. I'm going to clear your stuff. But on the next page, I'm going to break those down. So help me remember those percentages: 78.7, 15.1, 6.3. All right, so first of all, I want to look, here's the black. I'm not actually going to do it with the tools on the page. So 78.7 is going to be, it's going to be hard for me to get it right. I don't know, somewhere in that range. All right, now I'll just color that in. So that's approximately 78.7%. And I'll make sure I color code my stuff down here. So that's what no force looks like. It's red. The next percent was, remind me.
15.1.
15.1, thank you. So if I add 15.1% to that, to 78.7, I think it's gonna be like 93.8. Yeah, something like that. So I'm just guessing that's gonna put me about right here. All right, so you can see there's the 15% stacked up, which means the rest of it, which will be the higher force, will be blue, is gonna fill in right there. Okay, and I'm gonna quickly fill in just a little bit, just the first color for the condition of white, which was 84.4%, which is about right here. All right, I'm not trying to take too long doing this, so I'm just gonna talk about it really quickly. All right, so I mean, we'd fill in the other colors up above. So the whole thing with this, we're about to answer a question, and we'll come back to this. Well, okay, let's talk about it right now. We can see that there is a difference between these segmented bar charts, right? If I filled in the rest of it, it would not look exactly the same, right? There's a difference. Now, the question then becomes, if I skip ahead, does the data suggest that there is an association between the race of the suspect and level of force used? And when we're answering this kind of question, you need to make a claim that either there is or there isn't an association. And you want to support the claim by comparing at least two percentages between the groups and include the context. You got to say what it is we're talking about. Okay, so again, just to try and not keep you here forever, this is what a possible answer could be. You could answer it differently. But here, there appears to be an association between race and level of force used. For example, white suspects received no force from police officers at higher rates, 84.4%, than black and Hispanic suspects. Now, we don't have the Hispanic data right here, but we could have calculated it. So level of force is associated with the race of the suspect. And I'm going to come back to this. We're going to talk about one of the other concepts from the chapter. But is everyone good with this for now? Or if anyone's not good, if I could, you can raise your hand or chip and ask a question. So what I'm going to do is I'm going to go back to our presentation. Okay, we looked at contingency tables. So now we're going to talk about this, maybe one of the more difficult ideas in the chapter, independence. So variables are independent when their conditional distribution is the same for another variable's conditional distribution. And that might not mean anything, so let's look at some examples. And hopefully this example will clarify the concept. All right, so I've got, and this could be made up data, but it doesn't matter. Let's pretend it's real. So I'm gonna come down here and I'm gonna look at this conditional distribution. So on the condition of being male, what is the preference for animals? I'm not going to calculate this exactly. This is about 80%. And this is about 20%. So on the condition of being female, what's the breakdown? This is about 20%. This is about 80%. All right, hopefully you guys agree. So before I talk about independence here, let's look at the other chart, the other bivariate data. We've got on the condition of being male, you know, what is the distribution of passing in versus failing? This is 0.6 exactly, and this is 0.4. On the condition of being female, this is 0.6 and this is 0.4. So when we compare these two, all right, and this is the key idea with independence, we can see that in the first data set on the left, your gender, at least according to the data, will have a big impact on what your favorite animal is. So if I was to pick a random male, assuming this information is true, if I was to pick a random male, what would I guess their favorite animal is?
A dog.
A dog, right?
Dog.
A dog, yeah. And then if I were to pick a female, I would guess cat. Now, I compare that to on the right, and if no matter whether it's male or female, that doesn't change kind of the mental analysis that I do. They both have a 60% chance of passing. There's no difference between them by gender. So so on the left, these are not independent. So okay, let me say this correctly. Favorite animal is not independent of gender. Independent. Pretend that says independent, all right? That's not independent. And this one is independent. And what we means is that, I cannot write today, so there you go. That is independent. What we mean is that whether someone likes a dog or a cat seems to be associated with their gender, it's not independent of it. Whether someone passes or fails this class seems to be independent of whether they're male or female. Okay? So independent means that there is not an association. So no association. It's not an easy concept. It's almost counterintuitive in some ways. Like, yes, it's independent, but no, there's no association. Not independent means there is an association. Okay. So if you can read that scribble, that's the main idea. If you want to write something like that down in your notes as you're going through, that might be a section you want to go back and reread, make sure you really understand it. Okay. Are there questions on that right now? Okay. Then let's go ahead and we have one more thing to talk about, and then you can, we'll finish up. Now we had two more things, but we already talked about these. The only thing to add here with bar charts is that if it is relative frequencies, then they have to add up to 100. And notice that we've got these all adding up to 100%. You can see this is class of automobile versus drivetrain. So every car has some kind of drivetrain. It has to be 100% at the end. Over here, I don't know what the data is, but it's counts. So with counts, notice there's case B had far fewer cases than E. All right, so these don't have to be the same height. Mosaic plots, all right, actually there's a few more things to talk about than I thought. They are similar to segmented bar charts. That you're gonna read something tonight to really make sure you understand it. I will quickly go over this, the way you read this. The entire box right here represents 100% of the population of the sample that maybe what the sample represents. So that's 100%. And you'll notice right here, we've got almost like two bar charts, or sorry, two bars. So that's why it's like a segmented bar chart. And the left is male, the right is female. And that's how we split it first. We start at the bottom, all right? So after we split it that way, then we go up to, this is passenger class. I should tell you this data represents people on the Titanic their gender, their sex, their what kind of class they were sailing in, and then whether they survived or died. So now we split each of these up by passenger class. So these are all the second class passengers for females. These are the second class passengers for males. Notice they don't align perfectly because there was a difference. There were far more males in third class, relatively speaking, than females. Okay, so after we split it that way, then we go up to the top, and the top there's no label, but 1 means that they survived, 0 means that they died. Okay, so now we can answer the question. If I told you to find, in fact, I want you to do this. Get ready to annotate. Find the group of second class male passengers who survived. Okay. Yeah, once we get a few annotations and you hone in on the right spot. There it is. Second class male passengers who survived are right there. And now I'm going to clear all these drawings. And the last thing to mention about this is that this area of that rectangle represents the proportional amount of the entire population that we're talking about. So if we found the area of that rectangle and compared it to the total, it would give us the percent. So it's really good kind of seeing a visual on how the data breaks down. Okay, there's something about that in your homework tonight. All right, so I will clear all drawings. And we have one last thing to talk about. I know I'm keeping you guys here for a while, but hopefully in future days, that's not the case. So we got, oh great, let's stop annotating. I know you're probably doing it accidentally. All right, so here's one form of Simpson's paradox. And of course, here is the form that you guys will be needing to know. So sometimes the overall distribution of many categories combined is opposite of the average or the distribution within each category. So we need an example for this. This is a real case. The data here is a little bit mixed up, but don't worry, we'll make sense of it. This was California, Berkeley, the college, showed how many men were admitted to their graduate program compared to women. And this looks like a clear-cut case of bias, right? 44% of men were admitted, only 35% of women. And now we're talking about Simpson's paradox, because let's see, when you break it down by college, and we don't know what departments these are, that could be like science and like engineering and something like that. But when you break it down and look at the conditional distributions, how does the story change? And you can unmute and kind of say something to this.
Different departments have different acceptance rates.
Hey guys, let's stop annotating. Yeah, every department has different acceptance rates, and that's an important point to make. That's good. Because I mean, we can compare Department F to Department A, and which one's easier to get into?
It makes it seem that women are admitted more on average than men.
More or the same. Yeah, obviously there's a higher admittance here, but you know, I'd say, at least personally, the rest of it doesn't seem like there's major difference one way or the other. All right. So about equal for these, and then significantly higher actually for this college. So how does Simpson's paradox work? This is just something you need to recognize and understand the concept behind. So notice that the higher admittance rate departments, these top two, are preferentially chosen by men. So the men who apply are applying it seems to be preferentially toward these colleges that allow a lot of them in. And the women, and this is real data, though these numbers right here for applicants don't add up to 4,321. I don't know what happened, but this is a real story. Women preferentially applied for departments C through F with lower acceptance rates. So it's that's how this happens. Whenever, you know, if they had applied more for departments A and B, then we wouldn't have seen this discrepancy in the overall amount. Okay. So I know we've been here for over an hour. So just to wrap this up, here's your homework. You don't have to copy it down because it's on the Canvas page and you can work on this. I highly encourage you guys to go through and do the homework even though you're not going to turn it in. You need to make sure you go through it until you fully have mastered this and you got chapter 3 down.
Mr. Davis?
Yeah.
Last night I tried to look at the worksheet and it was blocked.
Yeah, and I'm glad you did that. I changed the way, because some people were letting me know, I changed it later in the mid-afternoon. So today that shouldn't be a problem. Last night, it's not that big of a deal. It was just categorical and quantitative, but thanks for going and checking.
Show.
So with the last little bit of time, if you feel like you understood everything we were talking about today, that's great. You can have a wonderful day. If you feel like you want to go through a few of the problems from the textbook, I'll just show this real quick. I pulled up 2 of these problems and I'm going to go through them. If you want to hang out, I'll go through them. It shouldn't take me more than like 5 or 10 minutes. But if you need to get away, you can find this video later to watch it. So at this point, if you are leaving, have a great day. If you are sticking around, I'll get started right away. Okay. Okay, so problems 22 and 24 in the textbook. You're not doing these 2 in your homework, but they're very similar to some that you will be. I'm not going to actually do all the math here. I just want to run through them as fast as I can. So students in an intro stats course were asked to describe their politics as liberal, moderate, or conservative. Here are the results. And it's a 2-way table. So what % of the class is male? Well, that's asking for a marginal distribution. So we've got male out of the 192. You guys can figure out what 115 divided by 192 is. Hopefully you're feeling good about that. Okay, what % of the class consider themselves to be conservative? Well, now it's marginal again, but we're dealing with the 27 conservatives out of 192. So notice that in both of these cases, we're talking about the class at large. Now the next one, we're going to be talking about conditional. Okay, so what % of the males in the class consider themselves to be conservative? So on the condition of being male, how many consider themselves conservative? What %? So it's going to be 21, not out of the whole class, but out of the 115. All right, now the last one here is a little tricky because it almost looks like it's conditional again, but what % of all students in the class are males who consider themselves to be conservative? Now we're not talking about a conditional probability. This is just an intersection of 2 variables. So we've got males who are conservative, and out of the total, 192. So that's going to be a 21 out of 192. All right, so any questions on that first part? Okay. 24 is referring to the same data set. And when you look at, like, I think problems 21 and 23, it's going to be very similar to these 2. Okay, so on the first is find the conditional distribution of political views for the females. So we want the distribution of political views. And so the condition is that you're female. So we're looking at this row. So it's a little bit tricky to identify which is the condition, but it is females being the condition on this. And I'm not going to go through and calculate it, but it'd be like 35 out of 77 for the first, and 36 out of 77, and so on. All right, for part B of that, the conditional distribution of political views for males, it's the same thing, just for males, okay? The graphical display that compares the two, now we're talking about making a bar chart. You would have gone through with A and B and come up with your percentages. Now this is where, because it's relative frequencies, you have to have those bar charts be in the same height. And you're gonna have a breakdown. I'm gonna estimate what it is. So this is 100% up at the top. And this is gonna be your females and males. And you'll need to get the exact percentages when you do your example problem like this. But 35 out of 77 is almost half. And if I look at the males, 50 out of 115 seems to be almost half. Okay, so I'll call that the liberal. Moderate seems to be about the same. So I'll just add another piece onto that. Okay, and then for the top, that should be the leftover, will be the conservatives. So I'm using different notation, symbology for each one. And so creating that isn't difficult, not too bad. But the last bit, do these appear to be independent? And here's what you're looking for. If these bar charts look wildly different, like let's say there was another bar chart here where tons of people were liberal, a few were moderate, and then there are some conservatives. So this one right here looks way different from these other two. But, you know, ignoring this one, because that's something I made up. These two, I have a feeling, you know, if you did this problem, it would show up something like this. Because there's no big difference, we would say that they appear to be independent, meaning there's no association between gender and political choice. We're not going to say females preferentially are preferentially liberal, males are preferentially moderate, or anything like that. Seems like that doesn't matter. So does that make sense? Okay. Then I will look at the next problem. And this one is none of these are as bad as they seem once you just kind of read it and wrap your head around it. CDC has estimated that 19.8% of Americans over 15 years are obese. The CDC conducts a survey on obesity and various behaviors. Here is a table on self-reported exercise classified by BMI. Okay, so the first question here is actually the only one we need to talk about. Because it says, are these percentages column percentages, row percentages, or table percentages? And if you read the chapter, you've already came across these terms. I didn't really talk about them in class today. But essentially what they're saying is, are we looking at a conditional distribution where the condition is your level of activity? And if it's a conditional distribution right here, then these rows would each have to add up to 100%. So these three numbers at the top would have to be 100%. These would have to be 100%, and so on. Now, I think it's pretty quick to see that this bottom row does not add up to 100%. So the condition that we're holding here is not physical activity. The condition appears to be your BMI. Because if I add these up, I do get 100%, and hopefully just a quick visual check you'll agree with that. So what we're saying is, on the condition of being normal BMI, what is the conditional distribution of physical activity? Okay, and that's kind of how this table was created. If none of these added up to 100%, then they'd have to all add up together to 100%, and it would be, this total right here would be 100%. So that would be a table percentages, okay? So knowing that, use the graphical displays to show different percentages of physical activities for the three BMI groups. So it's showing that the condition for our segmented bar charts, I'm not going to create this at all, except to draw three bars. So we're going to have normal, obese, overweight, and obese. And we'll have to break it down. And then just like before, we're going to be looking at this and seeing if these are these three, you know, the same breakdown more or less, or are they different? But there is a trick, and this is the last thing to talk about, and then you can head out. The question is kind of a trick question. It says, do these data prove that lack of exercise causes obesity? And in statistics, proof is a very high bar. And so we will have ways of proving, of showing causal effects for things later on. But right now, this does not prove anything. All this shows is that there is an association. So no proof. I'll just write it this way. So anytime there's proof, you know, we don't have that, but we do have associations. Okay. So you can say something to that effect, but no proof. All right. Are there any questions about this? Okay. There might be other questions that come up because this doesn't cover all the stuff on the homework, but you know, just look through it all and make sure you're feeling good, and you can always ask more questions. Okay. If you guys are good, that's the end of class. And if you have more questions, you can hang around. Have a good day if you're taking off.